Jeff, thank you so much for joining us as part of this lecture series. And it's great to discuss with you today about the effects of radiation and how we're expanding uh, our uses of space and what it means for crewed space exploration. So once again, thank you so much for being here.
Nope, you're welcome. Pleasure. Glad to be back, even if it's remotely at this point. So,
Yes. Uh, and we do hope to be able to do this in person, but having the recording is also great because then we can we have it to show many other people as well who can't actually be in a place in person.
right, no problem.
So we have this expansion of the uses of space with both the moon and Mars being areas of principal interest. And we have the Artemis program led by the United States that wants to put people back on the moon and to have a sustained presence on orbit and on the moon. You have the Russia-China pact that is also wanting to have crewed space exploration on and about the moon. As we're thinking about this challenge, there's the technical component, but then there's also the human aspect. And if we are thinking about having crewed space exploration, you know, the, the the distance healthcare component is a problem that's going to have to be solved, and part of that includes mental health, aspects as well as
Right,
physical health. And for
right,
the physical health, one thing that seems to boil right to the top is radiation. And that's exactly what you study. And so, why is radiation such an issue? What are some of the things that we have to worry about? And how does it compare with many of the other health aspects of space exploration, crewed space exploration?
gotcha. So I'll start off with the last one first because it's easy. Why is it such a big deal? Well, it's because it's one of the big unknowns, and NASA has prioritized it as one of the. I think there's 5 limiting technologies that are minimizing our capabilities to do exploration missions. And space radiation is one of the primary ones. And the reasons is it has been such a difficult problem and still is an emphasis because the type of radiation that you find in space as compared to what is typically found and what people outside of my discipline are accustomed to hearing about here on Earth is completely different. So first of all, you have a different type of interaction that causes damage either to soft tissue matter or to condensed matter like hardware, um, completely different than what a gamma or X-ray source that you typically find here in the United States, like either like a nuclear power source or the X-ray at the dentist or something like that. Um, and that makes it very difficult because when you're exploring, so we do know that radiation is problematic in high doses. That's not just there's no doubt about that. We have evidence of exposures from like atomic bomb survivors, the Chernobyl event, and other occupational exposures. But in each instance, that is a very unique type of radiation. It's either a high flux of neutrons or energetic gamma exposures. In contrast, the cosmic rays of heavy charged particles found in space are completely different in how they interact. Where for like a gamma or neutron, let me just throw that out, but gamma or X-ray exposure, when they enter the body, it starts attenuating and losing energy right at the skin. Um, Heavy charged particles or cosmic rays that are found in space are completely different, whereas they lose most of their energy at the end of their range. So where they range out is where they deposit most of the energy. So what makes like proton or carbon radiotherapy that is being used terrestrially to treat some cancers very useful is completely opposite for space radiation because one, it has a very non-homogeneous distribution of energies and damage in the body. And two, in science, when you try to study an outcome, the one thing that, especially in an experimental approach, you want to try to simulate what you're trying to recreate as accurately as possible. And that has been a technological limitation since the beginning of the space program and spaceflight itself. Most I can only think of one. I think, yeah, I'm pretty sure there's only one heavy charge particle accelerator in the United States that can provide ions that are similar to what is found in space, especially at the energies, and being able to provide not only all just that single ion energy, but all of that spectrum of all of the different species that are found in space. Right now, it's technologically impossible. The second flip of that, so that's the limitation technologically because of trying to provide the environmental analog. The flip side of that is the biological analog. Again, when you're trying to understand some type of health outcome, and frequently this is done in clinical medical studies, they either look at epidemiological studies of patients or humans exposed to a certain stressor, and they try to understand based on statistics what was the outcome, what were the mechanisms, how do we mitigate this. We don't have that same capability here on Earth. So a lot of the approach for looking at the biological model has been using either a rodent or a mouse, in some instances like a large animal like a Yucatan mini pig or a primate. But even then, it's difficult to go from, let's say, a mouse and extrapolate, blood kinematics to a human because they're not even remotely similar. It's 1/20th of the body mass, genetically very dissimilar, the metabolic rate, just everything is problematic. So when you combine all of these issues with just the analog in the simulation to try to understand what the problem is, it just, all the errors add up until it becomes almost untenable to try to translate what's going on in humans.
There seems to be also a timescale issue that has to be addressed, where some of the things that you notice, like atomic bomb survivors, uh, you have this one-time sudden injection of
Right.
energetic particles. Uh, with space travel, I mean, yes, we can have flares and different types of changes in the space weather environment, but they're always getting exposed to it at some level, the astronauts.
Right, and it's a much higher dose than what we're exposed to here on Earth, but it's definitely at a much lower dose rate than what they were exposed to, like in the atomic bomb explosions or at Chernobyl. So there is that inability to try to also model, well, does the body repair itself? Does the body adapt to this environment and actually um, figure out a way to survive? So that makes it another difficulty. So when you're trying to compare, the epidemiological studies of occupational or atomic bomb survivors to the chronic exposures of what the astronauts incur in space, there's another variable that just kind of
Yeah.
convolutes your data right there.
With some of the animal tests, are there clear takeaways that we have learned from all of that, or is it what we've learned is that this doesn't work?
What's the nice way of saying this? I would say we have learned a lot about what we don't know, and that's pretty much, I would say, everything. There is a lot of argument in this discipline and in my field that heavy charged particles or space radiation isn't even a carcinogen. So it will not incite cancer unless you're given it in a large dose. They there's a lot of thought that there's cognitive deficits because of these exposures, cardiovascular disease outcomes, but none of this has ever been seen in humans. And the way the models are done and the experiments are done in these animal models are sophisticated, and the analysis and the outcomes are very scientific in their approach. What gets convoluted is like, okay, so now how do we go from this mouse and how we studied it here? We gave it the equivalent of what we think is a Mars dose, so 3 years of space travel, but it got that dose in 15 minutes as opposed to 3 years. So how do we go from that to this is what's going to happen in humans? And it's just really just kind of convoluted. So I would almost argue that we don't, a lot of the research because science is built up on the shoulders of all of your predecessors. I wouldn't be able to even say that we really don't know anything unless all this research has been done over the last 30 or 40 years, because you had to at least try to figure out what you didn't know. And I would argue right now we still don't have a good idea.
Now, we do have the ISS, and we have
Right.
astronauts who've been going on longer durations there. So, what have we learned from the crewed exploration in low Earth orbit, as well as anything that we have learned from, say, the Apollo missions?
In terms of the radiation exposure, I would start to argue now, because I think, and you can actually look up. We released a paper about a month ago. We make this argument. There has been 500 or so humans that have flown in space, and I think upwards. I'm looking at the dose thresholds of more than 150, 200 that would, in all of our experimental studies, instigated either cardiovascular disease or a cognitive deficit 100% of the time in these animals. But this has never been attributed to space radiation or even diagnosed in any of the human crews that have flown on these long duration missions, some of which have been home for 5, 10, 15 years. So I would argue that those missions have taught us a lot, because it indicates that the human body is very adaptable. Maybe it's more robust than we give it credit for. Maybe the space radiation risk, at least at that very low dose rate, is overemphasized, and we need to reevaluate how we approach it. Maybe it's not the limiting factor. Maybe it's just the vehicle and the behavioral aspect of space that will be the worst part of it.
I want to get to the behavioral component a little bit later. Uh, Along this thread, much of that duration has been in low Earth orbit, and the radiation environment is different there from what it would be on, say, the moon. And so, kind of, what type of limitations do we have so far with our knowledge on that particular component?
So surprisingly, the radiation environment in low Earth orbit on ISS is not that much different than what
Okay.
you would find in interplanetary space. It's probably a factor of 2 or 3 lower in dose rate.
Hmm.
It's still pretty. So on average, ISS astronauts get the equivalent of, in 1 to 2 days, of what we would get from background radiation an entire year. Outside of low Earth orbit, you can take that and multiply it by 2 to 3 times. Um, so it's a much higher dose rate than what we're getting here, a higher dose. But there has been studies recently, as I think they published last year, that showed that the spectrum and energies of particles measured are, for the most part, very similar that what was found in a measurement from a telescope that is orbiting the moon right now, the crater
Hmm.
detector, and also the measurements from the Curiosity rover that was launched, I think, in 2012, and then landed on the Mars surface. So in each instance, the spectrum was very similar. So you could argue that there is a lot of similarity in what they're exposed to and on ISS compared to what the astronauts will be exposed to when they do start venturing out to the moon, Mars, asteroid, or what have you.
Now, as we do venture out uh, to those locations, uh, we're going to have longer and longer missions. And currently, NASA has limitations on how long astronauts are allowed to be uh, in space and exposed to the radiation environment. And I was wondering if you could speak a little bit to that and where you think this is going for these missions. At some point, it has to relax.
Right, and there's actually been effort to do that recently. So I think there was a presentation by the main entity within NASA, that the space radiation element. They do all of the human related risk assessment and research for NASA, and they've presented the concept of I think decreasing that limitation by as much as 40% for exploration missions to the National Academy of Sciences. Um, I think it was well received. I'm not sure what the decision was yet, but I would presume that they would follow the recommendations of what we're asking for. So that could become a non-factor here, at least that significant limitation here very shortly. Because if you look at that, limitation, for depending on the age of the astronaut, they could reach that within, a year and a half, 2 years. And so if you look at if you want to fly astronauts to the moon or Mars, you probably don't want to take a rookie or a first time flyer. You want someone with some type of experience of living in that confined environment, the stress of flying in space. But a lot of those flyers would probably be limited to how long they could fly, if at all, because of that burdensome limitation. And ironically, of all of the risks associated to humans for spaceflight, um, you can get on a vehicle and basically explode yourself into space. You can live in a pressurized vehicle that if you had a leak, you would be dead in just a very few minutes. But you can sign off what they call informed consents on all these risks, saying I'm willing to accept this risk so I can fly in space. That limitation, that 3% elevated risk of radiation-induced death, is a non-starter. You cannot sign off on that at all. So being able to minimize that and allow a little more leeway in that time and space will be a great asset to NASA.
Do you know how consistent the current limitations are among the different space agencies for their astronauts? Is there basically a generalized understanding of what the current limitation is, even if the idea is to eventually relax it, or is it each industry has decided on some number? Or excuse me,
So
that industry, I meant agency.
right. So most of the partner agencies do follow the standards set by NASA. It's our vehicle, so they have to follow those standards too. There was some gender-specific differences in terms of the maximum dose. NASA is also reevaluating whether or not those were scientifically valid or not. They were based on epidemiological studies of like atomic bomb survivors, Chernobyl survivors, occupational exposures, and a lot of it had to do with the increased incidence of breast cancer in females versus males. I do know that like the Canadian Space Agency, the Japanese Space Agency, and ESA have eliminated any gender specific differences. And now NASA, as part of their presentation recently to the Academy of Sciences, asked to consider lifting those same limitations because there's no evidence empirically of astronauts having a different risk based on gender itself. So, well, long story short, most of the agencies do follow the recommendations of NASA, and a lot of them is because they have flight rules, specific guidelines on space flight that operate how mission control manages a mission, and so that provides that limitation to all the flyers on NASA vehicles.
Is there any sense how this extends to private space tourism?
No, it's kind of a mess. In a good way too, because they may help us push the limit and show that perhaps this has been overemphasized for a long time, and we should put our resources and our efforts and research into priorities like propulsion, navigation, avionics, a bigger, better vehicle. It'll be very interesting, and I'm involved with 2 of those flights coming up here shortly. It'll be very interesting to see how a non-NASA astronaut adapts or reacts to the space environment. And I'm curious to see how the liabilities issues work their way out, because what if one of these passengers, they fly for a week or 2 and then 5 years later they get cancer, or they have some type of other cardiovascular related health issue? Do they have will they try to sue the companies because it's attributed to space radiation, even though there's technically no way to prove it? So it'll be interesting to see. I think they're going to be very surprised at how brutal the first couple of days of space flight can be. Most of if not all the astronauts I've ever met or talked to, they're usually sick for the first 2 to 3, 4 days, up to 2 weeks. So if you're going to be sick the entire flight and you spent millions of dollars, it may not be as much fun as you think it is.
It's not the joyride that they signed up
Right.
for.
Right. Take good video so you can remember it later when you feel better. Right.
Now, the spacecraft are actually designed with the radiation in mind and have shielding. So, what actually goes into that, and what can the astronauts be protected against, and what can't they be protected against?
So when you talk about shielding, especially like the operational space radiation environment, there's two specific scenarios you have to consider. That the galactic cosmic rays are these chronic exposure that we've been talking about, and then the anomalous events, the solar particle events that you mentioned earlier. For the most part, with typical spacecraft shielding, and I say we're almost to that threshold, you can attenuate a large solar particle event enough so that the astronauts are reasonably protected inside the vehicle. With the galactic cosmic rays, I don't know if shielding is going to be a solution. Simply because, again, it goes back to why heavy charged particles are beneficial for clinical radiotherapy, and while they're not beneficial for space radiation, more shielding can actually break apart these heavier energetic particles. And if you remember from your physics classes, the conservation of energy, all that energy that was in that one simple ion is now distributed between, 5 to 10 neutrons, a bunch of protons, and lighter charged particles, which can range out in the human body. So shielding actually can increase the dose that the astronauts can incur or make it less safe. And I think there's been studies that show even up to upwards. For instance, like the Apollo vehicles, the shielding was about 5 grams of aluminum, 5 to 6. There's been studies that show that there is 0 or no more attenuation if you have up towards of 100 grams of shielding, so 20 times the shielding capabilities of the only vehicle that has ever taken humans outside of Earth orbit. So, still a big issue.
Yeah.
Go faster.
On the surface of a celestial bodies, let's just say the moon for our argument, what are some of the precautions that can be taken, say, there as opposed to the spacecraft?
Well, first you got a good bit of the planet shielding. So the cosmic rays are isotropic, so they're coming from all directions when you're in space. So on the surface, you do have some shielding because you have a planet shadowing effect to eliminate a large portion of the spectrum. And that also for solar particle events, they have to be geo-effective so that they actually interact at the location where you're on the surface. Like for the moon, you would have also the capability of like digging down into the regolith and building additional shielding, use the mass of the lunar surface itself on top of habitats. Same with Mars. And you also have a slight magnetic field on Mars, which provides a little bit of shielding, but it's probably 1/50th of the magnetic field of the Earth, so not much. So most of your effort would be just taking advantage of the fact that the planet shields a good bit of the chronic dose, and hope that you get lucky and don't get hit with a large solar particle event, and you're able to dig far enough down to protect yourself with a lot of natural mass above you.
Yeah. Well, it does seem like the way that we're really going to make progress with this is to have people who are willing to go out there and be exposed in this environment and test it out. And until that happens, a lot of these questions that you're talking about, they don't necessarily seem like they're going to be answered, at least easily. But then my question is, what can change here from terrestrial experiments that would really change the way we can understand the risks of the radiation exposure?
So a couple things, and honestly, it is a difficult question to even answer. So to kind of toot my own horn, our lab has developed a way to simulate the majority of the galactic cosmic ray spectrum continuously and at the same time using current accelerator technologies. And we have 4 or 5 experiments related to cardiovascular outcomes and cognitive outcomes scheduled to start in this fall. So we'll start seeing results from that in about a year or so. But even that's problematic because we're using a mouse model, which again is not a human. So it makes it very difficult to be able to translate even those outcomes out to a human. But what we hope is that we'll see completely different outcomes than what they're seeing now by using a limited capability itself. And that will allow us to make further arguments that, hey, we have all these astronauts who have flown in the field. They've received doses that, equivocally exceed the threshold for these outcomes you're seeing experimentally. Now we're seeing different outcomes in a slightly more realistic scenario. I don't want to say more realistic scenario in the ground-based analogs. I think it'll add more argument to say we need to reevaluate. Maybe this isn't as big as a risk. And what we need is, like you said, more humans who will fly in it and see what the long-term effects are. That's the best test case we have, to be honest with you. If you remember in the 1500s when they used to go on these sailing exploration missions, and in the earlier times, it was understood that 50 to 75% of the crew was never going to come home, but people still went. They explored, and that's how we learned how to do it better.
Yeah, it is a tricky thing for, I think, a lot of people to conceptualize that,
Yep.
this is part of exploration.
Right. Right.
What is the metric? Do we even have one for when we know we're at an acceptable level of radiation dosage? Or maybe said differently, we know the body can handle the radiation. Like, when do we know that?
For an acute exposure, it's pretty obvious because you have prodromal effects,
Mhm.
nausea, vomiting, skin burns. But for these chronic effects, we don't know the threshold. There has never been a clinical diagnosis in humans for any outcome that's been attributed to space radiation. So we just don't know if there is an upper or lower threshold for how long they can withstand even that low dose environment. If you remember, there was the twin study when Scott
Mhm.
Kelly went up on the 1 year mission, and his brother was, I guess, the ground-based test subject. Um, and I'm pointing that out because to go back to the fact that we don't know a lot about what we think we know. It's believed that the telomeres in the cell, as you age, and we know this for a fact on Earth, as you age, it becomes shorter and shorter, and terrestrial radiation can actually accelerate that shortening. But ironically, Scott Kelly's telomeres actually lengthened when they were in space. I think they reduced back to the normal pre-flight sizes when he landed, but that indicates that maybe there is a conditioning, almost healing effect from microgravity environment or something like that. So honestly, we just don't know. We won't until we go find out. If you remember, in the Mercury program, they thought their eyeballs were going to float out. They weren't
Yeah,
sure if their
right.
eyeballs were going to float out. So there's a lot of unknowns, and we won't know until we actually try it. To be honest with you.
Oh, uh, for a lot of these, well, for a lot of the things that you discussed, particularly in this recent summary paper that you've had, uh, there's the clear sense that we're trying to understand the space environment's radiation implications for things like cancer and so forth. Has cancer research in any way benefited from a lot of these different studies about space exploration? Basically, is it a two-way street here with how the radiation research for space exploration is connected with cancer research?
A little bit. I would say it's more complementary on the terrestrial side to the space side, simply because it's a bigger discipline, more researchers doing it. I would almost argue that most of the space radiation research that we have done to date is more applicable to clinical radiotherapy than it is to space radiation outcomes, because the way they apply the radiation, this high dose, single ion, single energy beam is more similar to a clinical radiotherapy exposure than it is to a space radiation exposure. So I would say it's limited in terms of how much it complements each other, simply because the environments are so different.
Yeah. Uh, we've talked a lot about radiation, but
Uh-huh.
there's more at kind of at risk that we have to worry about when people go into space, particularly for the long term. I'd like
Right.
to, if you're comfortable going into some of those issues, I'd like to talk a little bit about that. So we talked
Sure.
about the radiation. What are some of the other kind of top issues that we need to be worried about when we have people having these long-term habitation on the moon, travel to Mars, trying to get established on Mars, and hoping you make it back,
Right.
if you plan to make it back.
Right. So what we have to worry about is everything, because you're taking a closed system with you. And if one thing we have learned about space flight is everything breaks eventually. And if you don't have a way of repairing it or replacing it or recrafting it, you're in trouble. I would, on top of, the things like propulsion and navigation, I would probably say nutrition and behavioral aspects, the isolation and the small area confinement of space travel is probably a bigger risk than space radiation, simply because you know, in order to sustain the energy, the daily caloric intake of a human, that's a lot of mass, a lot of volume. So you have to either be able to take it with you or be able to take enough to grow more with you in an environment that a lot of these plants or things that you would want to create may not be um, as fond of as you are, I guess, for lack of better words. The behavior part, I think that is probably the scariest for the non-trained um, astronaut. Everybody reacts differently to stress, and in some cases, you don't even know how you're going to react until you're put in that situation because it's a natural um, reaction to it. I would almost argue that that's probably a bigger concern for these non-professional space adventurers. I always tell people to, take four of your best friends that were forced on you, go into your closet, close the door, and live there with your friends for 2 weeks, and then see how much fun it is to live in that small and confined environment with minimal communication on the outside with people you may or may not like that much. Um, I think that would probably demonstrate to people why this is going to be so difficult for them.
I mean, in some ways, the lockdowns that we've had with COVID-19 have given people just a little tiny glimpse of what that might be like.
Oh, that's a
Uh,
great point. I never thought about associating that, but yeah, it's affected a lot of people mentally. Even I know myself. I've worked at home for 8 months before our university is back open, and I
yeah.
could see differences in my behavior. Even though I love my house, I don't mind being at home working. I prefer to be here. I get more work done, but not being around your friends, not having that ability to go outside and just interact with other humans does start to change your behavior, mentality, let alone your hygiene. Because when you're not around people, if you're too busy, you may skip a day or so of showering or what have you. So a lot of things involved there. But that's a good point. I don't know if anybody's ever pointed that out, that this could be a way of evaluating that also. I'll have
I
to
mean,
ask my wife that.
I mean, there have been, of course, very long-term, careful studies of people in isolation, but nothing that's just been so,
Massive.
yeah, to at least in recent history, to the extent that we have right now.
Right,
Um,
right. And I don't know the numbers, but I know there's been a lot of discussion at our university about some of the students who are undiagnosed depressed. And there's
yeah.
been, I think, a higher increase of suicides or attempted suicide. So obviously it's affecting people more than we expected.
So, do you have any sense how we're going to deal with whether various health issues on in these type of situations, whether it is mental health or physical health, uh, when you know, we can't just send somebody there. There will be somebody who could, uh, uh, potentially, be able to diagnose what's happening. People will be trained. in order to do these type of things. But there will be lots that people don't know about. There will be a lot of unknowns, things that which you were discussing. How will that actually be addressed when we have this distance between us?
I bet we'll just figure it out incrementally. Right now, I think the commercial spaceflight aspect of it is going to drive a lot of this initiative, and they'll figure it out little by little. How are they going to force that issue, and how are they going to make sure their customers and their people who are, their spaceflight adventures are protected and happy and safe. Um, I think that'll probably be our best advantage. Just like in the explorers in the
Mhm.
14, 1500s, a lot of those were commercial endeavors. So they figured out how to do it bigger, better, faster, cheaper. I think
Yeah.
just by trying it, we'll learn how to adapt to that.
So
I don't know of any other way other than just
yeah,
trying, because we obviously, we're still learning about how the body reacts in space itself. There's the problem with the change in pressure that causes eyesight to
mm,
differ. There's a clotting issue that was just discovered a couple of years ago. No one ever knew about. So we're still learning just about the simple things that we thought we had under control. So
now with uh, all of your work on radiation uh, and crewed space exploration, you know, a lot of it has been in the context with cooperation with NASA and so forth. Has um, any of the industry components that we've been talking about here, have any of them approached you or shown any interest in this particular problem, or how much attention are they paying to this particular issue?
a little bit so far. And I would say it's not that they're interested. I think it's been tough enough to try to build a vehicle on your own and get it to launch. It's easy to launch hardware into space,
Mhm.
because there's a risk involved, but most of it's monetary, or scientific if you have like a scientific payload. It all changes when you're flying humans,
Right.
because if there is a failure, you could have 4 to 6, 7 people, perish immediately. So I think a lot of their effort, I do communicate with them frequently. I have friends I've known who left NASA to go work with them, who I still consult with, and they ask me questions. As a matter of fact, we do have 2 experiments going on. The Inspiration 4 mission that launches in September will be flying a radiation detector payload on there to measure the environment and characterize it, which will be very interesting because I've heard they're going to have a unique orbit. And then we also have a detector being fabricated that's going to fly on one of the Artemis lunar surface missions. So we measure in the radiation environment on the lunar surface, hopefully by November, December of this year. But each way, their approach has been different. Dealing with the moon mission, where it's all scientific payloads and other hardware, it's been a cakewalk because we've been doing this for a long time, and the commercial spaceflight firms have a lot of history and knowledge to leverage to make this a whole lot easier to put something in space. But on the flip side, when you talk about SpaceX and the fact that they're trying to protect humans, there's a different level of caution and uncertainty, and just incrementally going, okay, can we get away with this? Can we get away with that? Can we get away with this? So they're aware of it, but I don't think they know enough about what they need to be aware of yet to really ask the questions. And I think probably something like space radiation, since they're not necessarily talking about long commercial spaceflight missions,
Mhm.
isn't their priority yet. But I think it will be very quickly, because if I understand the orbit of the Inspiration 4 mission, they're going to be really concerned about it very quickly. Let's just say that.
uh, is there anything from those type of discussions that have really that has really excited you about the possibilities that perhaps they're taking, yeah, there's a lot that they don't know, they're asking lots of questions, but they may also be taking completely different approaches to the problem then as well, that may lead to some advancement that no one's expecting.
Oh, yeah, absolutely. Because just going back to that Inspiration 4 mission, they're
Yeah.
taking, I think, 10 to 12 scientific payloads to do experiments in space, what I refer to as citizen science. So now we have another outlet to do
Okay.
rapid test of specific experiments that we may want to do to prove or disprove a theory very quickly, let alone another data set. Because now you have non-NASA astronauts. And if you're doing some type of health or biological study, you have a different data set that you can say, well, we're not seeing in astronauts, but they are the top 1% in terms of health, and they have 5 different doctors looking at them
Mhm.
24 hours a day, monitoring their health, and they have 2 hours a day budgeted into their timeline to work out on the ground, let alone in space. So now we have a different data set to look at that also and see, is there a big difference between the health of the person versus the outcomes we're seeing in space, or the age, because you're going to have a wide spectrum of these people flying. I think it goes from like 27 to 28 to in early 50s. But yeah, I think I think a lot of the development technologies and our capabilities in space will come from commercial space flight, not from NASA, simply because they have the capability to adapt very quickly and try new things with minimal risk or problems trying to re-steer the ship. So I'm actually really excited about that.
In any of these discussions, have you gotten into what emergency procedures might look like? They're out there, there's a solar event, and they have to do something. Uh, what, I mean, does that exist and what does it look like?
That's a good question. I have not. Um, and I'll probably bring it up eventually. I do know that SpaceX has leveraged a lot of the experience from NASA previously. So I would presume, so most of the monitoring for anomaly like that, like a solar particle event,
Mhm.
comes from the Space Weather Prediction Center. It's a
Yeah.
NOAA institute based in Boulder, Colorado. And they communicate directly with the airline companies, NASA, satellite companies to provide insight on any type of countermeasures that need to be taken. So I would presume that they are communicating them with that same um, line, so they'll have a heads up. What their procedures will be, I don't know yet. I've only been involved for about a month now, and we have to deliver, completely new payload hardware by mid-August. So it's been kind of a focus on trying to figure out how to do that. Usually, you have like a 1 or 2 year run up to get ready for something like this, and we have basically 90 days. But I think it'll come up pretty soon because there is, the sun's starting to get a little more active over the last couple of weeks. So it'll be interesting.
Uh, what are some of the procedures that are, done for, say, the ISS? Some of the existing procedures.
Yeah, so that's a good comparison, but also not a good comparison,
Okay.
simply because the orbital inclination and the altitude of ISS
Mhm.
and the amount of shielding it does have,
Yeah.
it's actually pretty well protected nominally for a solar particle event. But if there was an event, what would happen is we would get, if there wasn't a flight controller on the console actively monitoring, because they're not on 24 hours a day, you'd get a call from the Space Weather Prediction Center saying that there was a sizable event. Most likely, if it's a really energetic event, it's already at Earth because it's moving.
Yeah.
It's only what 12 minutes at the speed of light, and I think there was an event in, I think it was 2005, October 2005, where the energies were 80, 90% the speed of light. I think it was in low Earth orbit in like 15 minutes. So by the time you get and evaluate it, the astronauts have probably been in the environment for a little while. And typically, what we would do is make a recommendation to the flight controller to either interrupt the timeline or wake up the astronauts, and they would go to one of the more shielded areas of ISS. And that was typically like in the US lab over near where the treadmill is. In some cases, their crew quarters. So I would imagine that would be similar procedures, but for these vehicles are going to be flying, they're not going to have that shielding capability. And I suspect they'll be much more exposed because they're going to want to go higher in altitude so you can see more of space. And they're going to want to go at a higher inclination. So they're going to want to go closer, most likely, to the poles so they can go through the aurora and they can see the constant change of scenery by going higher and higher in latitude. But that'll also make them much more susceptible to these events. So if they're not planning on it, and have a contingency to either rapidly deorbit or not, they should have talks about that very soon. So it could be very interesting.
Yeah, no, it is. There are a lot of moving pieces with this. We only have a
Right.
little bit more time, and so I wanted to ask you, what are some things that you would like to bring up specifically that I haven't asked you? We've covered a lot of stuff already. Is there anything that you want to go back to, or some main point you want everyone to know with this discussion?
Um, Probably. I mean, so much. It's such a big
Yeah.
field. I'm honestly, I'm just really excited about where we are right now. If you would ask me 10 years ago, when I was just the old curmudgeon from NASA, who was just kind of not necessarily bored with it, but had been doing it for so long and hadn't been much change, I wouldn't have probably said it the same way. But just looking at the innovation and how fast it's accelerated over the past 5 years, we're launching a non-professional astronaut crew for a 4-day trip to space here in about 3 months. And I think that's an amazing feat.
Mhm.
And they're talking about putting a similar crew in orbit of the moon next year. And if you think back just 3 or 4 years ago,
Yeah.
you never would have said that was possible. And it is. They're going to do it. And I think they're going to be successful. So it's exciting to be part of that. Um, I think there will be a lot of um, changes in how we approach spaceflight itself and the radiation risk, because we have reached a point where some of the technologies and our capabilities have improved, and it could allow us to do different analysis. So I think over the next 4 or 5 years will be really exciting. I would like to put it to bed and work on something else, but we'll see. I can't. Other than that, I can't think of anything specifically. I do always like to remind people that space flight is expensive, but the amount of knowledge that comes from us trying to adapt, live, and and fly in this extreme environment has been amazing. I think a study a few years ago showed that for every $1 that NASA spent, it was equivalent of $3 to $4 spent on specific research like cancer or material science, electronics, stuff like that. So I would think that the commercial spaceflight aspect will accelerate that. What we're doing right now with SpaceX we're doing something it's probably going to be nearly impossible to do. But if it pulls it off, it really changes the way some of the hardware is used in spaceflight.
Mhm.
And it's because we're forced to. They gave us parameters and you say you can either do this or not participate. So okay, we'll try to figure it out so
Yeah.
we can participate. But that's how you accelerate change. And I think that's exactly what they're going to do is they're going to force the issue and make people think about a lot of this differently. Let's find a more clever way to do this.
You have a lot of exciting things that are happening with the work that you're just talking about earlier. You were talking about the the broader spectrum radiation that you're being able to produce with the lab. Um, kind of what are some of the very first tests that you really want to do with that broader spectrum, and kind of uh, and really kind of move forward with these tests?
The first thing I want to do, and I hope we're able to convince some of us, is I want to be able to recreate the spectrum at certain dose thresholds and get samples from astronauts pre, during, and post flight, and see if we're seeing those same markers.
Yeah.
Are we seeing? Are we able to instigate cardiovascular disease in this mice, and what dose threshold? Okay, so are we seeing these same precursor indicators in the astronaut blood or plasma, and be able to validate if it's a legitimate threat or not? That's what I'm really excited about. And lately, NASA's been talking about doing larger animals like Yucatan mini pigs, which are they're not humans, of course. Well, some humans you would probably call a pig, right? If you did, but their cardiopulmonary system and their dermal system is very similar to humans, so it's a good surrogate. So adapting that to like a mouse and also a pig gives us another data point where we can look at, if we compare it to the astronauts and their outcomes, are we seeing indicators that this is a problem or not? I think at the doses that we're looking at, we'll be able to make an argument one way or another on whether or not we should be worried about this risk or not. So I'm really excited about that. We've been working on this for about 5 years, and we finally get to start it doing real experiments on it in the fall and spring. So very excited about that.
Well, it's very cool research, and I really appreciate you taking the time to talk with us about this, to share your insight on space exploration generally, as well as radiation. And so I want to end it with this one last question, and that is, you alluded to, if you could solve this radiation problem or know the outcome of it, you'd want to move on to something else. What would that something else be?
Oh, I guess I should have thought of that, huh? Oh, I don't know. I do nuclear physics, so it'd be something with that. I would probably do something um, more in terms of our modeling capability and the computational aspect. We have slowly, my research lab has migrated to do what I call computational nuclear physics,
Mhm.
using supercomputers and machine learning to solve all these, or at least analyze all these problems. I'd probably um, look stronger into that, because I think the capability to put some dynamic model on 50,000 CPU cores and have it grind out what it thinks is a solution is pretty powerful, because you can't do a lot of these experiments in a laboratory. So you try to analyze as close as you can the reality computationally. So I'd probably do something like that. But that's a good question. I haven't really thought about it, because that's all I've done for 25 years.
Well, when you have a high fidelity computational model, it can really open doors, as you're
Right.
saying, because now you can address a whole host of problems that otherwise you were really limited to just what was available within the observable data. We always want to be kind of comparing things to reality, but once you produce that high fidelity model, you can go to regimes that you otherwise can't explore, at least
Right.
currently. So
Yep. Exactly. Yeah, you just small perturbation around some normal and see what happens, to try to um, just kind of understand nature. It's half the
well,
fun.
once again, thank you so much for your time today and for talking with us. And I know we'll be hearing more from you soon.
Sure, you're welcome. Thanks for having me again. Looking forward to it.
Take care.